Alright. Alhamdulillah, wassalatu wassalamu ala rasulillahi wa ala alihi wa ashabihi ajma'in wa ba'd. Alright, so let's get started with our new topic of indices, surds and logarithms. So this thing is very important, especially for those who are pursuing your A-level mathematics, because this is the foundation for trigonometry. This chapter is the foundation for trigonometry, and trigonometry is the foundation for differentiation, integration, differential equation. So if you don't have a solid foundation here, you will suffer consequently in all of the following chapters. Alright, so indices, we already know about all of this from previous course or previous study. First we'll have that as a recap. So in indices, in addition or subtract, no properties related to powers apply ever. Okay, so we know that if we have same base and we multiply them, then we can add their power. If we have the same base and we divide them, then we can subtract their power. And if we have the same power, we can take that power common and add and multiply the individual numbers. And similarly, if we have a common power between multiplication or division, we can split them. So a by b to the power m can be written as a to the power m and b to the power m. So this is the quotient. In addition, subtraction, no properties related to powers ever apply, which means a to the power m plus a to the power maybe n. You can't do anything here. There isn't anything related to this. Similar for a to the power m, negative a to the power n, and same for a to the power m plus b to the power m, a to the power m minus b to the power m, and so on and so forth. Okay, so you know why? Because a plus b to the power m, let's say I am simulating this with this formula, a plus b whole square, which is not a square plus b square. Is a plus b whole square, is it a square plus b square? No, it's plus 2ab. It is a plus b into a plus b. And then what happens? You multiply a with the whole thing and then b with the whole thing. Okay, so that's why do not make this mistake. Okay, this is an error. And you already know that if you have a to the power m n, like this means m into n, and if anything is something like, let's say 2 to the power 3, and that is power to, I think, maybe 8. If this is the case, then you can multiply m and n. So here we have 3 multiplied by 8. You already know this, right? So you already know this a to the power a to the power m, and if that is to the power n, then we can multiply the powers a to the power m into n. Okay, so that's the slight revision. Okay, so you can take power common in multiply and divide, but do not take power common in addition or subtraction. Okay, you can't do these things. And I've already talked about this. Okay, now about negative powers. You already know this, right? X squared and then to the power 4 is not x to the power 6. You don't add here, you multiply them, x to the power 8. If it happens in the case of negative powers, which is the reciprocal of the base changes, if you want a reciprocal, if you have the reciprocal of the base, then the plus minus sign will be changed. I mean, there will be a change in sign. So a to the power negative b, a to the power negative m, if I want to write in a reciprocal way, I would write 1 upon a to the power m. And look at this. If I'm flipping the numerator and denominator at the cost of reversing the or changing the sign of the power. Okay, and you know that anything to the power 0 is 1 to the power anything is 1, and basically root of anything means that things to the power half, cube root means that thing to the power 1/3, and so on and so forth. So can we say that m root x is basically x to the power 1 by m?
Yes. Yes.
So if we have x to the power 3 by 2, then we can write this thing as root of x cubed. So you can think like this way. First take the cube and then the half. Okay, so if we have x to the power m by n, we can write it as n root x to the power m. Okay. Now we move on to Surds, which basically means square roots. When we simplify, let's say we have a root 8, and we want to simplify to the least possible, I don't know, least possible, most simplified manner. So what do we do is we think of largest square factor of 8. What are the factors of 8? 1, 2, 4, 8. Largest square factor of 8, which is 4, and we write it as a product of that, so 4 into 2, and then we can split this root to 4 and 2, so we can write root 4 into root 2. Root 4 can be written as 2 square, so this thing becomes 2 root 2. Okay. Then we have root 27. These are the factors of 27. Largest square factor is 9. Write it as 9 into root 3. 9 can be written as 3 square, so this becomes 3 root 3. If it is 180, largest square factor. See, 4 is also a square factor. 9 is also a square factor. But we want to take the largest square factor, which is 36. So you write 180 as 36 into 5, and from here we get root 6 square into root 5. So ultimately this things brings down to 6 root 5. You can try this in the calculator as well, by inserting root 180. See that the calculator gives you a value of 6 root 5. Okay, this is the case with simplifying Surds. If we were to add or subtract, let's say we're adding 3 root 7 plus 5 root 7, so because you have the same root, you can add them, you can take root 7 as common, so that would be 8 root 7. If you have something like this, 2 root 8 plus 5 root 2, what happens? You can't add now root 8 with root 2, so change this root 8 to root 2 first, which is 4 root 2, and then add with 5, making it 9 root 2. So this is how we do addition and subtraction. And for the multiplication is the same thing as like how we multiply algebra. First multiply everything, like first multiply 3 with everything on the second bracket, and then multiply 2 with everything on the second bracket, and like this is what you get. Okay, any confusion so far?
No, everything is fine. Thank you.
Alright, now for divide, there is something peculiar. Maths people do not like square roots in the denominator. So that's why when you have square roots, you will have to rationalize. What is it? It is a process of shifting roots from denominator to numerator. Let's say if you have a root of 3 divided by root 2, you will have to take this root away from the denominator and take it to numerator. So what we do is we multiply root 2, like we multiply a fraction that has the same thing in the numerator and numerator, so that gets cancelled out, becomes 1, and then we know that root 2 multiplied by root 2 is 2, so ultimately this root 2 is now, as you can see, is shifted towards the numerator. Okay, if you want to find cos 45, actually it is 1 upon root 2, but if you have to rationalize and give it in the most simplified form, you would use the rationalization, and this thing would become root 2 by 2 cos 45. Okay, we'll learn more on the exact values of trigonometry later on, hopefully, inshallah. And yeah, now what if you have something like this? Up until this point, it was pretty easy. Just multiply with the root of the same thing, in the numerator and denominator. But if you have something like this, how would you know what would you multiply? Well, you multiply the conjugate of the denominator. You multiply and divide with the conjugate of the denominator. What is the meaning of conjugate? Well, just change the middle sign. The conjugate of this thing is this thing. Both are conjugate of each other. Okay? So you have to multiply this thing with the conjugate so that a minus b, a plus b, they are being multiplied. We can use this for identity. A square minus b square equals to a plus b, a minus b. And now we can rewrite this as a square. So root 7 square minus 2 square, that ultimately becomes 3. If you make the calculations, you have to show the process. I'm just ignoring the calculation, and ultimately you would be successful in removing the so-called hated surds from the denominator, which is what we don't want. Are we good so far? Now we move on to logs, which is basically the short form for logarithm. What is logarithm? Basically the inverse of exponent. So we know 2 to the power 3 is 8. So now logarithm basically tells you to what power, if you raise a base, you will get the answer. It is basically the inverse of exponent. That's why you have the inverse relationship between exponential and logarithms graph. Okay, inverse relationship. They're inverse of each other. You remember it from function, I guess. So when do we need logarithm? When indices fail. What does that mean? So if we have 2 to the power x equals to 8, we can rewrite 8 as 2 to the power 3, and then we can equate the power because the base is the same. But what if I tell you 2 to the power x equals to 11? You cannot use indices now. When you can't use indices, you have to use logs or logarithm. So how does that work? If you have a exponential form or index power form, you have to take it into log form. How do you do that? You these things would swap, and you have a log of base a. Basically, this is a shortcut. Actually, what we do is we introduce log to the base a in both sides. If we introduce log of base a to both sides, what happens? We know from logarithm property that when the base and the arguments are equal, these things become 1, and x can be written outside as a multiplied. So that's why x equals log base a argument b. Okay, but in a short form, if you wanna make this fast, just flip the x with b and the log of that base. So basically the base remains the same, the base of the exponential and the base of the log stays the same, and then flip the other things, if that makes sense. Yeah, that is what we do in logs. Now we will yeah, do you have any questions?
No.
Key. All right, so না কোশ্চেন না থাকলে করার দরকার নেই, টাইম নেই। Okay, so in mathematics actually there isn't anything called like moving this thing outside. I know in our childhood we were told that when this thing gets that side, that becomes plus thing, but actually that doesn't exist. We actually do the same thing on both sides. So this thing means we add both sides plus 2, we add both sides 2, and then these things gets cancelled out. Eventually you get the result. So this is what we call preserving equivalence in mathematics, a basic that I felt to share. So you know that yeah, I just show you the derivation of how this thing got. Okay, how actually I got from here to here. Introduce log a to both sides, and so on and so forth. So if we have exponential form and you want to convert it to log form, this will be this thing. and 5 to the power 2x equals to 8 would become 2x equals to log base 5 argument 8. Okay, now we have some important rules about logarithms. Okay, so regarding this is what we call the base, and this is what we call the argument. Argument must be cannot be equal to 0 and cannot be negative. It should be greater than 0. Cannot be 0, cannot be negative. Base is the same as argument, cannot be 0, cannot be negative, but cannot be 1 as well. Cannot be 1 as well. These are the rules, because logarithm is basically the inverse of power of exponent. So 2 to the power, so if I have log base 2 argument 8, you know what does that it represents? If I to what power of 2 if I raise, that would become 8. So the reason why you cannot have 0, like you're asking to what power of 2 if I raise will it become 0? You cannot make this 0 regardless of whatever power you do. 2 to the power anything, can it ever be to 0? Anything power to the 0 is 1, so it cannot be 0. So that's why, because of these kind of mathematical rules or facts, you have to comply with or obey these rules. Okay, so yeah, do you have any questions?
I do not have any question. Thank you.
All right, so we move on, but before I want to address why the base cannot be 1. So what is the meaning of log base 1 to anything, which means what power will I raise to 1 to become, let's say, 2 or 3 or 4? Well, 1 to the power anything is 1. That's why base of 1, a log of base cannot be 1. And I don't remember what is the meaning of this, why did I write, anyway, yeah, so we have learned how to convert from exponential to logarithm form, and we should be also be able to convert from logarithm to index form, the reverse step. This is very important for your differentiation and integration. Yeah, this is the same thing. Why it can be 0 as well. 0 to the power anything is equals to what? 100. 0 to the power n equals to what? The logical thing that I have taught previously to explain why these values are not accepted in the log operation. Yeah, so you also have to be proficient in converting from logarithm to exponential. So if you have, let's say, log of base a argument b equals to x, then you have to convert it to index form like this: b equals to a to the power x. You just switch the b and x. Okay, so if we have log base 2 argument x minus 1, what do? How do we remove log?
We remove log by dividing by log in an equation.
We don't divide by log.
Oh, you use the formula. So here it will be x minus 3 is equals to 2 to the power 4.
How exactly did we got here mathematically?
because in here when he it's log base 2 x minus 3 is equals to 4. That means when you raise 2 to the power of 4, you get x minus 3. So you can if you write that down as it is, 2 to the power 4 is equals to x minus 3. You get it.
Well, basically we multiply here log base 2 to argument 2. That means that this is log 1, and then we put this log here, 4 here, and then we cancel out log 2. This is the actual way, and the shortcut is actually just reversing this thing what you have said, but this is not the actual proper mathematical way of equivalent, preserving equivalence. Anyway, from here you can find the value of x, okay, which is 19. So you will have these problems, and you should know that log base anything is 0, and when we have the same exponential, same base, log base anything is 0. Argument could be anything, 1 or anything, whatever. Log base anything is 0.
Like argument 1
You can try it in the calculator. Put log base anything, argument 1, right? Yeah, if you have argument 1, regardless of whatever you put forward in your base, it would be 0. Log base 2, argument 1, 0. Log base 3, argument 1 equals 0. And if you have the same argument and the power, it is equal to 1. You know the power rule of log, that if you anything to the power in the argument can be written as n multiplied by log base a n. Now do not make this mistake. This n must be to the power of the argument, not entire square of the log, okay? Or I mean, to not entirely multiply to the with a square bracket, with a bracket, not square bracket. Anyway, so if you have log base to argument log base to argument x to the power 7, you can write it as 7 into log base to x, and vice versa is also true. If it is in this form, you can also bring it this form, okay? This is the mistake. If it is so that it is 3x squared, you cannot bring this 2 here. Why? Because this square is not entirely on the argument. If it is that it is 3x whole squared, then only you can do this, okay? This is the power rule for logarithm. Also, if it happens that the power is entirely in the if it is something like log base a 3x and then whole square, also you cannot bring this down. Only it is power of the the argument, okay? This power rule applies only for this. Then we have the addition and subtraction rule. If we add logarithms of the same base, arguments gets multiplied. If we subtract logarithms of the same base, arguments gets divided. For these to apply, there must be no coefficient behind either logs. So which means if it is so that this thing minus 2, it won't work. You will have to take this here, y square, for this to occur. So this is a very important line. For these to apply, there must be no coefficient behind either logs, okay? Example, you cannot use this you cannot use this rule yet. You have to bring these terms using the power rule here, and then because we are adding the same logarithm with the same base, we can multiply it, and ultimately this things becomes this. If it is something like this, the same thing, except for it is being divided, and the final answer is the same. Okay, and vice versa is also true. If you can go from here to here, you can also go from like here to here as well, but take a caution, do not make this mistake. If we have something adding in the argument, then you can't do anything. Same for subtraction. If you have anything multiplying with the log, then that is nothing. Same for the logarithm. So do not make any mistakes like this. And this is an advanced property of logarithm which is used in differentiation and integration only, I am giving you some spoiler, like of that topic. Even though it's not, even though it's not necessary at the moment, but it would be required in differentiation and integration. Do you have anything to say? All right, that's great. So let's move on to more advanced topic. So you know the difference between rational and irrational number. So basically rational number is any number which you can represent in pure fractions, which means the denominator and numerator is integer. Okay, any number that you can represent as pure fraction is what we call as rational. Pure fraction means the numerator and the denominator are integers. Root 2 cannot be expressed in as a pure fraction. That's why it is irrational. Same for pi. It's never ending, unlimited, infinitely going on the decimal. Okay. Any number that can be expressed and converted into a pure fraction, that is rational. Any number that cannot be converted or expressed as a pure fraction, that is by definition irrational.
I have a question. So, are all numbers that are irrational have a non-repeating number sequence like pi, or is it just something exclusive to pi?
What about root 2?
Yeah, root 2, I'm just asking whether the repeating, are there any repeating sequence when you evaluate root 2 as a decimal?
Recurring numbers, like it could be something like it is repeating 1 to 5, again 1 to 5, again 1 to 5.
Yeah, something like that.
Alright, I think that question is not relevant right now. We just have to know what is rational and irrational. That is a huge topic, else discussion. And you also have to know the difference between real and imaginary. Real means anything that you don't have I or iota. If you have something like root over negative number, that is not real and stuff like that. So, logarithms have different bases. If we have the base 10, we call it special logarithm, common logarithm. If it happen the base is e, which is Euler's number, a constant 2.718 blah blah blah, that is called the natural logarithm. And in book paper you would find it like this, log base 10, but in calculator it would be lg. If it is log base e, log base e in book and calculator both, where you would find it as ln. So ln e would be 1, because following the logarithms base and argument same rule, that gives you 1. So yeah, if you want to solve a particular equation, using either of them does. But if you have something like e, this should give you an indication that I need e, like ln would be helpful to cancel out the e. But otherwise, let's say if you have an equation 2 to the power x equals to 11, and it really doesn't matter whether you use lg or ln, because ultimately you would find the same answer, as you can see here. Just you have to introduce logs to both sides and you'll get the same answer. So please reflect upon this for a few seconds and let me know whether you have understood everything here or not.
Very interesting thing actually.
No.
Okay.
I do not have any problem.
All right. That's great. So now we move on to problem solving. So, like, this is a very structured way of solving. This includes very detailed guidelines, so that you don't have to waste any time in your exam. You practice with these guidelines and you become like not a nerd, but like you become a super robot. Whenever you detect a particular pattern, you just follow these steps. So type 1 questions, if they follow if they follow these conditions, then we term as type 1, and this is the method to solve them. So if you have one term on either side, no logs on either side, basically we introduce log or ln on both sides. For for this, you introduce ln or log on both sides and solve. For here, you would want a ln because that is e. We want to cancel out e, so that's why we take where is it? Sorry. That's why we take ln. Okay. If we have something like these, it really doesn't matter whatever you take. So can you please try to solve these 3 questions and tell me what is the answer of x?
Of course.
Of course. I am done with the questions. The answer to the first one is 3.459. The answer to the second one is 0.805. The answer to the third one is 0.386. These are the type 1 questions. As for the type 2 questions, the answer for the first one is 13, the answer for the second one is 52, and the answer for the third one is 2.13. Hope that concludes today's class.
Alright, that's great. All your answers have matched, and this is the end for this session of today, as you have hoped and expected. We will continue with the later portion in our next session, which